All right, I'm rather overwhelmed to see such a large turnout. I was expecting those who had passed, qualified from round 2 to round 3, the juniors. Are all the people in this group have all qualified to round 3? David?
I think so. I did send the invitation only to third round learners, juniors.
Oh, that's very nice. So we got a large number of people. I think they are a little bit concerned that they didn't have any.
Can you hear me, Prof?
Hmm?
Can you hear me?
Yeah, I can hear you.
Oh, okay, I did send to all third round junior learners only. I didn't
Okay,
include.
great to see. I've got 50 people here.
They share the link with the
Right.
others.
Thanks very much for that, David. All right, can you guys all hear me?
Yes, Prof.
Yes.
Okay, good. Oh, Nicholas, glad to see you. And yeah, Nicholas wrote to me and thanked me for the assistance we had given in the first earlier this year. All right, today I sent out the 2018 round 3 paper, and I don't know whether you had enough time to have a look at it. You know, my usual appeal is that you go through the questions before you come to the class, so that when you see the answers, you are not seeing the question and the answer at the same time. So let's hope that you had actually gone through these questions. You didn't have much time, but you are on vacation, I presume. So I suspect that you would have had a chance to look at them. Okay, now I'm just trying to. Oh, all right, I didn't get my pen connected. Okay, the very first question. Let's get on with the task at hand. We have 2 hours this time to do 15 questions. And these questions would be a little bit more difficult than the ones that you saw in round 2. Some of them will be non-routine, and you haven't seen such problems before. But certainly there will be no trivial problems in this final round. Okay, so you got the first question here. Which one of the following 5 prime numbers is the average of the other 4? All right, so now you've got 5 numbers, and one of them is the average of the other 4. All right, presumably what you have to do is, at the first guess, is try to take 4 at a time, work the average out, and see whether that number that you have taken out is indeed the average. Okay, you can do it like that. Let me just get into the writing mode. Okay, so you might say, well, let's remove 19 and work out the average of these 4 and see whether it's 19. And when you work out the sum, you have to work out the sum of the 4. And I think it is 60, 77, 136. And the average of those 4 numbers is 136 divided by 4. And that is certainly not 19, it's 34. Okay, so you could do it like that, and then try the next one, take it out and find the average of the other four and see whether that is the same number, or you can do this and so on until you exhaust all of them. And if luck has it, you might come and hit the jackpot quite soon before doing all the others. But if it's the last one, then you can imagine there's a lot of calculations to be made, because in each case you have to add four numbers, the remaining four numbers divided four, and you'll have four such sets if this happened to be the last answer. Okay, but some of them you can eliminate. Like obviously 59 can't be the average of those four. The average of those will be um, something in between. It can't be as large as 59. All right, that's one of the ways of doing it. But there is a calculation-wise, there is a much shorter way of doing it. What you do is add all.
Well,
Yes.
I will say that now. There is a you calculated like if you were the 19 were to be the average, and then I like from that 19 minus 2, which is 17, but and then that would mean 17 would cause that the number wouldn't be divisible by 4 completely, and then 19 plus 10 equals 29, which but then 10 is not divisible by 4, so then 29 also falls out. So then we have only 31 and 19, which can be answers because 59 is above the others, which means it will also fall out.
Hmm. I don't know whether I follow your logic, Andreas. You have eliminated many of them just by, are you saying you can eliminate all these very quickly? Because you said 19 minus 17.
Then the last four together gave you 136,
Yes.
which is divisible by 4. So then we can look at 17, which is 19 minus 2, and 2 is not divisible by 4, which means 17 cancels out. 29 is 19 plus 10, and 10 is not divisible by 4, which would leave 29 being cancelled out also. And 59 is also, of course, cancelled out because it's larger than the rest. So then we have only 19 and 31, and the only one that will work is 31.
31. All right. So what Andreas is saying is that the four numbers which must be added should be divisible by 4. And he's finding a quick way of deciding whether those four numbers, whether the sum of those four numbers is divisible by 4. And then if it's divisible by 4, then that means the average will be a whole number. All right. And all these are whole numbers. So the question is, I'm not sure whether I followed his argument, but um, he had a quicker way of finding out to eliminate 29, 17, and 59. All right, and a more advanced way is if you want to see if four numbers are divisible by 4, then you can divide each one of them by 4 and get the remainder. So when you divide 19 by 4, 31 by 4, and write down the remainder, this gives you a remainder of 3. 14 times 4 is 56. And all right, then you look at sets of 4 numbers which actually give you a remainder of 4. If I eliminate this 3, these 3 add up to 8. I think this is what Andreas is saying. So this is a candidate. And if you look at this 3 here, of course, for the same reason, the remaining ones is 8, which is divisible by 4. So this is a candidate. But this one here, you have 3313. And when you add them, you get 10. And that's not divisible by 4. So this can't be a candidate. I'm sorry, this can't be a candidate. And the same thing with this one here for the same reason. And this 3 can't be a candidate again because 3 and 3 6. Oh, but this 29, 59 could be a candidate because if you eliminate this out from there. All right, anyway, I think those are more complicated ways, but the easiest way is what I was saying. Well, it's not the easiest. I think Andre's got an easier way. What I would do is I would add the whole 5. And when you add the whole 5, you get 155. All right? And so the average of the whole 5 is 155 divided by 5, which is 31. All right, so the average of all 5 numbers is 31. So if I remove 31, the average of the remaining one will still be 31. Okay, so 31 is the answer. See, the average of all 5 is 31. So if I remove 31, the remaining numbers will also have to have average 31. So that's another way of doing it. Or if it didn't work out so easily, then instead of adding 4 numbers, you add 5 numbers, and in each case, you subtract that. 19, 155 minus 31, 155 minus 29. These will give you the sum of the remaining numbers. So it's easier to work out a simple subtraction sum than adding 4 numbers. Or you could use mathematics and you say, okay, suppose x is the number that you're looking for. Suppose you remove x, where x is one of them. So what are we saying? We are saying that if I remove x, the sum of the remaining numbers is 155 minus x. And the average of those 4 numbers is 155 minus x. 155 is the sum of all 5 numbers. Right? So when I remove x, the sum is 155 minus x. And we want this to be x. We want that average of the remaining ones to be the one that you removed. And this will give you the answer straight away without any further calculation. 155 minus x equals 4x, and 4x plus x is 5x. And that gives you x equals 31. So the number that you have to remove is 31. Okay, so as we saw, there are many ways of doing this problem, and it's allowed for a large number, a lot of discussion. Okay, let's get on to the next problem. Okay, so this is the solution which I just said now. Okay, here, question 2. What is the largest power of 2 that divides into 20 to the power of 18 without leaving a remainder? All right. By saying without leaving a remainder, it means that it goes exactly into it, right? The question is not nice. There's always a remainder. It could be 0 or 1. But I guess we have to interpret this thing to say that what is the largest power of 2 that goes into this? So you've got 20 to the power of 18. Now this actually, there's a very important factorization which occurs. And it's a kind of thing that people will probably ask in the 3rd round. You know, normally when you factorize a number.
View the chat column.
Yes, Andreas?
View the chat column.
Okay, I didn't get what you said, but please ask me the question after I finish with this, and then you can make your comments. If we...
Just view the chat. CHAT.
Yes, what about CHAT? Oh, okay. I must view the chat. All right. I'll look at it later. Andreas, please don't disturb me while I'm right in the middle of this. At the end of it, after I finished, you can ask your question and make your comments. All right. Otherwise, we will go on till 8 o'clock here tonight. Okay. Now, this is what I was saying, that you can take any number whatsoever, like 204, and you can always write it. Normally, you can factorize this thing into its prime factors. 2 squared, 4 goes into this 51 times. 51 is 3 times 17. So this is the factorization of this into prime powers. Right? Every number can be factorized into prime powers. So you have like 968, and that is 2 cubed times 11 cubed. You can check it out. So you have every number can be written as a product of powers of prime numbers. But the factorization that often happens is where you take the largest power of 2, which comes out, 2 squared, and that is 51. You don't factorize this. But what you say is that you can write every number as a product of an even number and an odd number. Or otherwise, a power of 2 times an odd number. And the 51 is the largest odd factor of 204. This is the largest odd factor. So if you want to find all the odd factors of 204, you look at only the factors of 251. You see? Like if you want to look for all the odd factors of 968, you will look at only the factors of 11 cubed. You must ignore the 2 cubed because those will, if you include the factors of 2 cubed, you're going to get even factors. So if you're looking for odd factors of a number, you'll take the largest odd factor, and that can be done by removing the highest power of 2 out of this. So this is what you do here in this case. This is 2 squared times 5, 20. 4 times 5. And when you take that out, you get 2 to the 36 times 5 to the 18. And this is an odd number. All right. So the highest power of 2 that divides this is 36. Right? Without leaving a remainder, whatever that may mean. Okay, now Andreas, can you come in now? Andreas, can you hear me?
Yeah.
Yeah. What is it you wanted to say?
Chat column.
The chat column. Oh, you want me to read the chat
column.
Oh, okay. Look, I can't see the chat column where I am. I have to get out of the screen and go and see it. So I usually do that after 3 questions, 3 or 4 questions. Then we'll ask for comments. All right. Let me do one more, and then we can ask for comments, and then I'll read the chat column. Okay. Now the next question is the following. Let's get to that. And here, so there's a long story here. In this paper in round 3, there are no multiple choice. It's not a multiple choice paper. And secondly, you have to write out your proofs. That might be quite a challenge. So you have to practice actually writing out a proof. And to do that, please go and look at my book. There are lots and lots of problems there, and you will see in every one of them, I've written out, the proofs or the solutions in a certain language. So try to get accustomed to the way you write mathematics without simply writing equations. Especially if there are proofs involved, you have to have some logical sequence in which you argue it so that you come eventually to the end of that argument. So in this case here, this is not a proof, but it says here, Futoshiki puzzles originated in Japan, and the word Futoshiki means inequality, which refers to the fact that the value of some cells on the board are forced to be greater than an adjacent cell. So if you look at this one here, for instance, we are saying that this number is greater than that number is greater than that, this is greater than that, and so on. So there are many inequality signs. You can read these as greater than, or you can read them as less than, depending on which way you are looking at it. Okay, so the idea is to fill in the squares so that each digit from 1 to 4 occurs exactly once in each row and column. All right. Now, let me leave this open to you guys. We can all do it together. It might be quite a chaotic situation, but one at a time, hopefully. Can we fill in any of these squares? All these numbers, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4 occurs only once in each row and each column. So we want to fill in all these squares. We've got only 3 here. So is there any square that we can fill?
We could do the one to the right of 3.
Yeah. Okay. Let's put it as, so we'll speak about these squares as, we'll say 1, 1. This is 1, 1. First row, first column. What will this be?
1, 2.
Right. 1, 1, 3, right?
3.
Okay. What will this be?
2, 3.
2, 3. This is a good practice because when you go to university, you're having what you call matrices, and this kind of thing comes up often. What will this be?
4, 2.
4, 2, right. Okay. Now, so you are saying that you can fill which one?
The one to the right of 3.
Yeah, okay. That, in other words, you're saying 3, 4.
Yeah.
So let's speak our language. Okay. Now, what are you going to put here? You can put 1 or 2.
Yes, but we have to put 2 because the one below it has to be
Smaller.
smaller.
All right. You can't, if you put 1 here, you can't get anything smaller here. So you have to put 2 here. All right. And this is naturally, it has to be 1. Okay. So let's proceed from there now.
And then to the right or left, the other side of the 3 dust, there must be an 4.
1 and 4,
which
right?
is 10.
So it has to be 1 and
4.
4.
Yes,
And 1
so
is smaller
yes,
than
1
4.
and 4.
Right. And likewise, what about this?
There we can just go with this.
And
So 4 is greater than 3,
4 is
and
greater than 3.
it's only that can be only one side or
Only
left
one
for
solution,
this
right?
row or column.
Okay.
So
So that's good. Now let's see if we've got, do we have 2 pieces of information in any one row or column? No, we don't. So now what do we do?
4, which is next to the 3, there we can have and 1 and 2, because if you have 2 and 3, it would
Okay, you
work,
cannot
or
have,
and 3 and 4 won't work. So we can have and 1 at the top and below it and 2 or
okay, so
above
you
that
can't
4.
put 3 here. This is important. You can't put 3 here, right?
Yes,
You
and
can't
you
you can't put 4
cannot
as well.
put
You
4,
can't put
and
4
you
as well.
cannot put 4.
So you can only put 1 and
So
2 here, right?
yes, so
So this
there
has to be
at the
2,
top,
and that is
yes,
1.
and then at the bottom of the add column,
Okay,
will it
Andreas,
have to be
I'll get
3?
somebody else to say now. Anybody else wants to carry on?
so, and then 4, 2, you have to put a 3 because of the column is, because it's 1, 2, 4, and 4.
Okay, I have to put a 3 here. All right, let's give somebody else a chance now.
Sir, above
So the
the
second
original,
row.
Okay, Aiden. Aiden?
so right above the original 3.
Yeah.
Um, no, between 2 and 3, sir. Second row.
Okay, yeah, right, okay. Yeah, what do you want to put here?
That has to be a, so that has to be a 1 because the square to
can't
the
it be a
left of the
4?
2 can't be a.
Why can't this be a 4?
Sorry. Oh, sorry. It can't be a 4 because a 1 can't go to the left of the 2 because
Oh, I
there's
see.
another 1
Yeah.
below.
Okay, so this is not 1. Okay, rather go to this then.
Yeah.
This is not 1. It's not 2. It's not 3. So it has to be 4. Because 2 and 3 already in, and 1 is already in. So this has to be 4. Okay, I think you guys are on the way with this thing here. I don't think there should be a problem with filling up all these things now. Now it's very much easier. Okay, let's just do one more before I open it out to discussion. We'll go to question 4. And question 4 is, all right. So this is question 4. Just read the question in the meantime. So a positive integer is to be placed in each box below. Integers may be repeated, but the product of any 4 adjacent integers is always 120. So any 4 integers which are next to each other, the product is 120. Determine all the possible values for x. Okay, anybody wants to have a go with this one?
Between the 2 and 4, will there have to be and 3 and 5 or 1 and 15?
Okay, what Andres is saying is that these 4 numbers, they multiply to get 120. So these 2 are already 8, 2 times 4. So these 2, the product will have to be 120 divided by 8, which is 15. So it could be 15. You need 2 numbers which multiplied gives you 15. You get a 1 and 15, or 3 and 5, 15 and 1, 5 and 3. So there are 4 possibilities.
But the pattern is repeating and there's a 3 at the end, so it has to involve a 3 somewhere.
Can you use that fact?
You should be able to because after every 4 squares, the numbers repeat again. If you put like any 2 numbers, you would see that it does.
The product of every 4 numbers repeat. Okay.
For
So
example,
how do you use that? Tell me.
we just take the 3, 4 steps at a time backwards.
Oh, 4
Then we
steps at a
see
time.
that because it repeats every 4 blocks.
Then how do you know it repeats? I don't understand.
I just tried putting like any 2 integers between 2 and 4.
Okay. Okay, so you did it by trial and error?
Yeah.
So can I
All
say
right.
something?
Right, okay,
So-
Almas.
So it repeats because like, so if the 3 are the 3 of like, let's say 2, 3 and 15, let me just use that. So and then 3 and 15 and 4, and then the next has to be 2 because it still needs to be 120.
Okay, we're getting there somewhere. Almas, that's a good observation. So what she is saying is that, so if I call this, okay, in general, this is the point here. Suppose I take 5 squares next to each other. We call this A, B, C, D, E. Now A, B, C, D, what's A times B times C times D?
120.
What is B times C times D times E?
120.
That's also 120, right? Now you can see these cancel off. Now that's what Almaz was saying, but she was taking a special case and she came to that conclusion, but this is the general result, that because the product of any 4 consecutive integers is the same, then the A, the first one, will always be equal to this one. So in other words, these numbers repeat after every 4 steps. That is something that somebody already intuitively decided. So that the person said, after 4 steps, this was a 3 here, right? And here, after 4 steps, this is a 2, right? You have to miss 3 in between and they start repeating themselves. So 3 in between, 2, 2. 3 in between, 3, 3. So now you've got 4 consecutive ones and you can see what X is. Right? Got it? So the point is you use the fact that the product of 4 consecutive numbers is the same, and immediately you have a nice little equation here, because 4 consecutive numbers, and if you take 5 numbers, then you can see that this product equals this product, and B times C times D will all cancel, and you have A equals E, which means the first is equal to the fifth. Okay, so let's ask now how things are. How's it going? Do you have any questions, any comments to make? Let me just stop sharing and talk to everybody. Okay, guys.
I actually had a question.
Yeah, Mehmet?
If we were to use silent as to solve a question, would we be awarded full marks?
Oh, you see, you have to show working, and if you made some little slip, I'm not sure whether they give part marks in this. I would think they would, because you have to show your working, but you have to have a reasonable argument. And if there's a little calculation error, they probably would remove. But they are quite strict. They might remove 2 marks or something like that. Not as in high school. So they are quite hard, because they expect people not to make calculation errors. But if there is an error in logic, then you don't get any marks. Okay, so Joshua, you said originally 2 to the 72. Do you understand why 2 to the 36 is the largest power of 2 that goes into it now?
Yeah, I was thinking that it's 5 times 4, and for some reason my brain thought that 4 was 2 to the power of 4, not 2 to the power of 2.
Oh, okay. Okay. All right. Well, Nakshatra, she guessed 5 was the answer, and 5 turns out to be the correct answer. So, but you have to prove it. You see, here in this case, you have to prove it. If you just run an answer is 5, I think that's the question that people ask. And if there are 3 marks or 4 marks for it, they'll give you 1 mark, because they say that you guessed it or you did it by trial and error. You have to do it the way I did it to prove that every 5th number is the same. Every 5th number, not by trial and error, but prove in general that A is equal to E, regardless of what the numbers are, whether they're 2 or 5 or 3 or whatever. Okay, so that is the way you do that one. Okay, are you happy with that? All right, so let's just go on, and if there are no other comments. Now the next problem is it's a geometry problem. ABC, okay, so you've got a triangle ABC, and D is a point on AB, as you can see. Let me So, and then you got 2 points. D is a point in AB. So from D, you draw a line parallel. So you start here, you draw a line parallel to BC. And from here now, you draw a line parallel to the third side. And from here, you draw a line parallel to the other side. In other words, just keep drawing parallel lines. That's interesting. Eh? I'd like to find out what happens when you keep going on like this. I've never tried it. Go up and then draw another parallel line here and draw another parallel line here and draw parallel and keep going on. Where do you end? Interesting. Or would you end at all? And if you do end, under what conditions where should D be so that you end? I can ask some interesting questions on this. Anyway, that's just a digression. Now the question is, prove that AD is equal to BG. You need to show that AD is equal to BG. All right, so if you want to show that AD equals BG, it's the same as showing what? Tell me. DG is common, eh? So if you want to show that AD is equal to BG, if you remove DG.
If you were to look, if you were to try and prove, I will say we should try and prove that AGE is like the same to BGF. I don't know the English
Okay,
word.
please, Andreas, answer my question. My question was, you are moving off the track. We are saying you're required to prove that AD equals BG. Let's look at what you're going to prove. Right? Instead of proving that this whole line is equal to this whole line, right, we might as well just remove this common part and prove that AG is equal to DB. Right? If you prove just that part equals that part, then we can come to the conclusion that BG, you simply have to add DG to both sides, right? And you will get AD. So do you agree that it is sufficient to prove that AG is equal to DB? Do you all agree?
Yes.
All right. Now, we've got a lot of parallel lines. AG, okay, let's start here. Let's not, so let's start here and see whether we can get there. Now, is this BD, is it equal to anything in this picture? So we're going to start here and try to end there to say they are equal. Is BD equal to anything in this picture?
EF.
EF. All right. BD equals EF. Now, let's see. Who said that? Just say it again.
EF.
Right. Tess, why do you say that BD equals EF?
They're both on the line DE and BC, so like they're equal.
That's not necessarily the proof.
Because BDEF is a parallelogram.
Ah, right. Who said that? Say it again.
No.
No. Why do you say that it's a parallelogram? How do you know it's a parallelogram?
Because it was mentioned that BF is parallel to DE.
And
that BD is parallel to EF.
Yeah, you need both of them. The opposite sides of this quadrilateral are parallel. Therefore, it's a parallelogram. The definition of a parallelogram is a four-sided figure where the opposite sides are parallel. Right? So if you have just one pair of sides parallel, it's a trapezium. Okay, so now that's important. You are given that these sides are parallel, so you can conclude it's a parallelogram. That's very good. So now we've got DB is equal to DE because they are opposite sides of a parallelogram. So when you're writing this thing down, the first statement you will say is in quadrilateral BDEF, DE is parallel to BF and BD is parallel to FE. Therefore, this figure here, BDEF, is a parallelogram. And therefore, BD equals EF. There is a theorem in geometry which says that the opposite sides of a parallelogram are equal. It's a theorem in geometry. Right, so these are equal. Right, now, Andreas has raised his hand. What do you want to say, Andreas? Okay, now we need to get to AG, remember. So now we ask ourselves, is FE equal to AG?
Yes.
Moed?
Yes.
Tell me why, Moed?
Yes, Prof.
AEFG
Sir,
is a
because
parallelogram.
Okay, Moed, AEFG is a parallelogram. For the same reasons, right? It's given. In brackets, what would be the reason? AEFG is a parallelogram. What would you put in brackets?
Basically, AE is parallel to GF.
And
AG is parallel to EF.
that's what you will write in brackets, correct. Right. And therefore, the next line you will say FE is equal to AG. And what reason would you give here?
opposite sides of a parallelogram are equal.
Very good. Right. That's a theorem in geometry. Opposite sides of a parallelogram are equal. So Moed, so now we are at that stage. We started here, we landed here, these are equal, and therefore you can add this small piece to both sides and you will get AD equals BG as requested. Are you happy with that? So that is
Yes, sir.
yeah, that is the way we do geometry. Okay, unfortunately, we don't have enough problems in geometry, but at some point, I would like to see, maybe we can have a nice session with only geometry problems. Okay, now we go on to question 6. Question 6 says, all right, there's a long story here, but I'm going to just tell you briefly what this thing says. I'm hoping that you would have read this question before. So what you have here is you've got 4 chests. I'll just put that down as 4 rectangles. Okay, and you've got labels on each of these chests. Now, each of these contains one item. You've got sand in one of them. You've got gravel in another one. You've got pebbles here. And you got gold. So you got one of them has got sand, one of them got gravel, one of them got pebbles, and the other has got gold in it. But you don't know which one has got which. But each box is labeled. So if you look at this now, three of the 4 treasure boxes are labeled. One treasure chest says gold or sand. So let's put this. We'll put G or sand. That's the label. So what this means is that this thing has got gold or it's got sand, right? And in the end, they say that all the labels are correct. All the labels are correct. They're not lying. Nobody's lying. This has got gold or sand. And the other one has got pebbles or gravel. I can put P/G. And another one has got gold or gravel. Gold or gravel. Okay, I can't put G now. I'll put GR, gold or gravel. And the last one has got no label in it at all. All right, now Molly is allowed to look inside. I'm looking at this last line here now. Molly is allowed to look inside one of the treasure chests before making a final choice. So she can open any one of these and look inside it, and then she can say she makes the choice. But her goal is to find the gold nugget, the one which has got gold in it. So she's allowed to open any one. She's got 4 choices. She looks inside it and she sees what's inside it. And based on that, she must now decide on go straight for the one which has got a gold nugget. So the question is now, which chest must she select in order to arrive at some conclusion?
So the unmarked chest.
You'll say it's the unmarked one. Okay, before we go there, let's see what happens if we take one of the others. Okay, suppose I look into this. I will see either pebbles or gold, right? So if I see pebbles or gold here, if I see gold.
So it's pebbles or gravel.
Oh, it's pebbles or gravel, is it? Oh, thank you. Right, thank you. Okay, so I will see either pebbles or gravel. Now, if I see pebbles, for instance, I cannot come to any conclusion. But if I do see gravel, then I can conclude that gravel is not here, so therefore this is gold. But if I see pebbles, I cannot come to any conclusion. Do you agree?
Yes, sir.
Right. So there's a problem. Yeah, I wouldn't look into this because I may see pebbles. Do you agree? Okay, likewise, if I look inside here, if I see gold, I'll be very happy. I said, okay, I'll hit it. But if I see sand, can I come to any conclusion?
No.
No. So this too is out because I cannot make any conclusion by looking inside here. So you got a 50% chance of picking the right one. Now what about this? I could see gravel here. And then I will say, hey, gravel is not here. I can make a conclusion. And say, therefore, this has to be pebbles. So I got gravels and pebbles. But now you cannot go any further because this is gold or sand. The other two are gold and sand. So you still don't know. The gold could be here or it could be there. So even this is eliminated. So now, who said go to the empty box? Was it Nicholas?
It was me, sir.
Aiden.
Aiden.
Right, Aiden, right. You said go to the empty box. And tell me why you said go to the empty box, Aiden? You can say because I've eliminated the other 3 boxes, right? Okay, but now we know we eliminated the other 3 boxes by logical argument. I hope you followed that argument. And now we are at this. Now, how do we actually decide where the gold is? All right, so I look into the empty box. What do I see? I can see sand, or I can see gravel, or I can see pebbles, or I can see gold. Right? Agreed?
Yes, sir.
Now, if I see gold, finished. I don't have to take my second chance. Okay, I've got the gold. Okay. Right, now let's take the other ones. If I see sand, suppose I see sand here, what's the conclusion?
Gold will be in the first
Yeah,
box.
let's call this A, B, C, D. Right. So if I see sand, I can find my gold. Right. If I see gravel,
Gold will be
in box C.
right, okay, that's fine. If I see pebbles,
Again in
Gold will be in box
C.
C.
if I see pebbles, what's the conclusion? First conclusion, what will this have?
Gravel.
Right. The gravel is here, what will this have?
Gold.
Gold. So I can still find the gold, right? So in all possible cases, I can find the gold by looking into the empty box. Are you happy with that one? All right, let me just check it out. Come on, you guys, if you understood that argument, please raise your hands. Oh, I can't see any hand. Oh, I see. Okay. All right. So I got 29 people raise their hands, which means 26 people did not follow my argument. Or either that or they too lazy to respond to my request to raise your hands. Oh, some of the lazy ones are shining up now. Okay. Okay, but it seems that there are some people who didn't follow the argument. But do it again. Go back home and go and check this thing out. Take each one and see whether you can make a conclusion. If you cannot make a conclusion, then get on to the next box. If you cannot make a conclusion, get on to the next box. But you will find eventually that you can make a conclusion with the empty box and figure out how you can make the conclusion. The only tricky part in that one is where okay, I don't know what happened to my diagrams. They all seem to have gone, but I can use the other one. Yeah, the only tricky part here was that if you looked inside here and you saw pebbles, or no, if you saw pebbles, yeah, then you got a problem. Then you can say, well, therefore this will have to be gravel, and gravel is here, so therefore gold is here. So you have to take all the 4 cases and go through each one of them and eliminate them to finally get to the answer. So this is a process of elimination. Okay, you can put your hands down now, and then we can get on to the next problem. The next one says, now going to problem number. Yeah, I think this one here. Okay, in 1250, okay, I'm not going to read this thing. I'll explain to you what this question is. This question, I don't know whether it's true, but I've heard it said before, so it's possibly it is true. The person who discovered chess, I don't know whether the same guy discovered chess, but the other part of the story is true. What he said was he had a chess board, all 8, whatever, right? And he went to the ruler of the land and he said, look, because I've discovered chess, you can pay me for it because this is such a great game. And all I want is grains. And he said, you can put 1 grain only in the very bottom square. And then after that, just double it. And then give me all the grains that you have in the chessboard, right? Double it to fill up the whole thing. So there are 64 squares, and give me all the grains that you have on the chessboard for my effort to create chess. So it turns out here that the number of grains on the last square is this huge number here. Right? This is far more than the number of rands which were stolen in state capture. Okay, how many digits has this got? It's got a number of digits. 1, 2, 3, 4, that's 12, 13, 19 digits. It's got 19 digits in it. Okay, so the question here is now, if this is the number of grains on the last square, the question is, what is the total number of grains of rice on the entire board? That's an interesting question. All right, so you are given the number of grains on the last square. Okay, now there are 10 people who raise their hands. Let's see now, one of you can tell me why you raise your hands? Or you're still answering the last question, or you? Okay, I see people are putting their hands down very quickly, but there are still six people. Is there any suggestion on how you can work out the total number of grains in the entire board if you know what the last one is?
Yes.
All right. Who answered that?
It's me.
Okay, Mehmet, what do you suggest, Mehmet?
I was looking into it. I was trying to add some powers of 2, and I came up with a formula.
Okay.
It says that 2 to the power of n equals 2 to the power of n plus 1 minus 2.
Okay, that's very, very nice. So what you did was, okay, the first one has got 1 in it. The second one has got 2. So you want to work out the total number of grains of sand. So the next one has got 2, and the next one has got 2. We'll put 2 squared, right? 2 cubed. And all the way, you need to calculate this. 2 to the power of 63, isn't it?
Yeah.
Because the index 1 starts here. So you got 64 squares altogether, right? So it has to finish at 63. 1, 2, 3 up to 63, and including that one. Okay, now the question is now, can you calculate?
There is a little bit faster way than to do that then. If you were to go, all of these together would be 2 to the power of 64 minus 1. Like,
Yeah.
if we were to look at 1 plus 2 is 3, which is 2 squared minus 1. 1 plus 2 plus 2 squared is 7, which is 2 to the power of 3 minus 1.
All right. Okay.
1 plus
Andreas,
2
yeah. Okay,
plus
I
2
got you.
squared.
He's seeing a nice pattern here. Right? I'll repeat what you were saying, Andreas, because some people might not be able to hear you clearly. What you are saying is 1 plus 2 is 3. That's 4 minus 1. And then you say 1 plus 2 squared is 7. And that's 8 minus 1. So you are saying if you use that idea, then 2 to the power of 63 is 2 to the 64 minus 1. That's what you are saying. And you know this. And you want to calculate that. This is the last square, right? This astronomical number here is this number here. It's on the last square. And you need to use this to calculate that. How do you do it?
So you times it by 2 minus 1.
But 2 minus 1 is 1. You wouldn't get anywhere.
I said you times it by
Oh,
2.
yeah, you times this first. You double this and then subtract 1 from the answer. Right? If you double this,
Well, if I were to say you calculate 2 to the power of 63, then the number of grains of rice divided by that answer times 2 to the power of 64.
no, that's being too
If I
far-fetched.
were to say leaves it to be that the number of grains on the last square times by 2. And then also there's a minus 1, so
Yeah, that's
minus
exactly what she said.
2
Andreas,
to
you're
the power
repeating
of
what the previous
63
said.
times.
Andreas, you're repeating what the previous girl said. Don't do that. She said times this by 2 and subtract 1. And that's exactly what she said earlier on. Okay, now the question is now, is that fair? Just by deciding, by looking at a few like this, you come to the general conclusion. Will that be correct? That the same pattern is going to work. How do you know it's going to work elsewhere? Now, I'm going to show you how to do it, right? It'll always work. And now this is proof. Now, in the third round, you will have to know how to prove it. Don't use, you will get maybe half the answers if you do it like that and you say, well, I can see 1 plus 2 is 2 squared minus 1. 1 plus 2 squared is 2 cubed minus 1. And you do it for 3 or 4 times or even 5 times. And you say, therefore, this thing here is 2 to the 64 minus 1. And you can calculate this from this one. And you do it like that, you would not get full marks, but you would get a fair number of marks. So I'm now going to show you how to get full marks. To get full marks, you say, let me calculate this. Let me call this x. I don't know what this is equal to. Right, let's call it x. Now the trick is you multiply x by 2, right? You get 2x. 2 times 1 is what?
2.
2. I'm going to put that under this. Plus, what is 2 times 2?
4.
2 squared, right?
Yes, yes.
Right. I'm going to put that under this. What is 2 times this?
2 cubed.
I'm going to put that under that, right? And what would I put under this?
2 to the power
2
of
times this
64.
will be 2 to the power, the 2 times the previous one will be 2 to the 63. And I must still multiply that there by 2, and that is 2 to the 64. Okay? Got it? You're multiplying everything by 2, but this is, when you multiply this by 2, you get 2 to the 64. And when you multiply the previous one by 2, you'll get 2 to the 63. Now the trick is you subtract the smaller one from the larger one, 2x minus x. Right. Subtract 0 minus 1 is minus 1. Right? Cancel, subtract, 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 and you land with only this survives, 2 to the 64, and there you have it. 2x minus x is x. That's what you're looking for. And that is equal to 2 to the power of 64 minus 1. And that's exactly what you said. But now we have calculated this thing without any guesses. Are you happy with that proof? Do you agree that we didn't guess? We've actually proved it. That x is 2 to the 64 minus 1.
Yes, sir.
Right, Almaz, yeah, okay. You see, now this is an interesting problem. It's a special case of something else. If you had, the point about this particular problem is that each term is multiplied by the same amount to get to the next term, see? So if you started off with, you didn't have to start with 1. If you start with a, right, and you multiply it by the same number, say call it r, to get to the next number, and you multiply this by r to get to the next number, you keep multiplying by the same number, then you get a sequence, and such a sequence is called a geometric sequence. sorry about the writing. Okay, and the very nice thing about the geometric sequence is that you can actually calculate maybe the 64th term. For instance, here, the second term is AR, the third term is AR squared, the fourth term is AR cubed, and the 64th term will be AR to the 63, right? And if you want to add up all these things, you call it X, just like as we did it here. You write down A plus AR squared and so on, just the way we did. But this time, you multiply on both sides by R, right? Yeah, we multiply by 2 because the common multiple was 2. Multiply by R, and then you subtract and you will get a nice formula. All right, okay, let me go on because we are losing time. I might have to go to much more than what I'm 6 o'clock, but I hope you will bear with me.
Can I quickly ask a question?
Yes, Mehmet.
While proving something, could I use something that was already proven to prove the question?
Yes. If you know, like for instance, you can use a theorem. In geometry, you can use a known theorem in geometry to prove something because that's in geometry, they prove it. It can be proved in geometry. And if it's something that you know to be true, you can use it. But if it's something that you are guessing to be true and you say, well, it's proven, then it's not right. You have to prove it first before you can use it. I don't know whether that answers your question, but you can't just guess and use your intuition. Okay, so the next question is another nice question in geometry. So what this says here, you got this diagram here, and C is a center of this large circle, C, and B is a center of this other circle, right? And you've got D is a point on the circumference here. So what happens is D is just a point on the circumference, and this center is joined and produced to hit the other circle. Then this thing here is joined to the center and shot off like that. Well, D and E are chosen to be points on the circumference. Okay, now the question is now, you've got only one angle given. You are given this angle here, 12. You're not given X, you're not given Y, you're not given Z, but you are asked to calculate those three angles of triangle ABC. You're asked to calculate X, Y, and Z, given only this angle. So now that's an interesting problem. I will have to go into my whiteboard to redraw this thing. Let's just hope get a nice picture going here. You got 2 points D and E. Let's take one of them. And then you join it to the center here. Where the center is. Oh, let me draw a straight line. Now, what happened here? Oh, I've knocked out my colors, I think. Yeah. So you go up here, and then you take this and you join it to the center. So you join that to the center, and then oh gosh, this is supposed to be the center of my circle. All right, it's not going to be coming out very nicely, but
Awesome.
anyway. Well, this is going to be the center of my circle. And then you've got this triangle ABC. I forgot what are the symbols. Okay, ADBF, ADB, DEF. Okay. So we go back to this diagram. Still struggling with this thing. So you have oh, okay, look, I'm not going to try to do this like that. Let's just mess up this diagram. Sorry about this, but let's use the diagram here. It's not working. Okay. Now, we've got only one angle, and that angle is 12. And our goal is to find all three angles of this triangle. So it's an interesting problem. Okay. Now, is there any place where we can start? I know that C is the center of the large circle, right? So that helps me because that means all the radii are equal. So there are two radii which are shooting out from C. One is CA and the other is CB, right? So CB is equal to CA. It's the center of a circle. Okay, so what can you say about Y then?
Whiteboard.
Y
So
must be
it's
equal
the
to?
white form.
What happened here? What will Y be equal to?
X.
Yeah, because CA equals CB, right? Therefore, this is an isosceles triangle. So this part here is equal to X. So I can put an X here. Now that you got an X there, can we make any progress? These two are X. This angle here, we can work it out in terms of X. What is it?
It's 180 minus x divided by 2.
Very good. So you have to, and what's the reason for that?
Because angles in a triangle add up to 180, and that's an isosceles triangle.
Why is it isosceles?
Because E to B is equal to D to B.
Why?
Because both of them are radii of a
Right.
circle.
Right. You see, I keep asking why until you come to something which you know. When you are writing geometry, you start from the know and go to the unknown. If you just write it down like that, it can very well be that you are guessing that you always have that equal to 180 minus x. So it's because BE equals BD. So you'll start off when you're writing the proof, you'll say BE equals BD. Reason, radii of a circle. Then you will say, therefore, these two angles are equal, right? You will say that, and then you will say that this angle here, x plus twice this angle, twice angle BDF, is 180 degrees, because x plus this, but these are equal. So x plus twice BDF is 180. So therefore, if you make angle BDF the subject of the formula, you have to take the x to the other side. And this is twice, that's why I divide by 2. So that's where you get angle BDF. This angle here that I'm pointing to is that. But that is also equal to something else in this picture.
Sir?
Yes, Neo?
Because of exterior angles of triangle AFD, you could say that that angle and then angle DEB is equal to x plus 12.
Very good. So she noticed that this angle is also the exterior angle of this triangle here. Right?
I think D angle BED and CEF is equal because then two straight lines and then they are like against each other.
No, well, we can talk about that later on, Andreas, but I don't think that's a logical conclusion. Look, we are at the stage here now where we have an equation involving x, and you can solve for x.
I don't know the reasoning in the English version of the reasoning, but D angle DED equal to angle CEA.
C, D, A.
E C
I'm sorry, I cannot hear you. C?
like the
I'm losing you. Andreas, I can't hear you. There's a problem with the mic. There's a resonance. I can't hear you. All right. Let's hope that gets right, and we can come back to that. So here you can solve for x. This is the usual way of solving it. I'm not going to go into all those details, but I guess quickly I can see 2x plus 24 is equal to this, 3x is equal to this, and x is 52. I see that x is equal to 52. And once you got x is 52, then you got this is 52. You need to work out the 3, and this is 52. And you got 2 of those angles. And therefore, you can work out the third one, which is the third angle of the same triangle. All right. Andreas, you want to speak to me again, and I'll try to see whether I can hear you?
I was saying angle BED is equal to angle CE.
BED equals?
BED.
Yeah, is equal to?
CEF.
CEA. CEF.
Sir, he means vertically opposite angles are equal.
Yeah.
That's what he's trying to say.
Yeah. But then, how does that help you? You must move towards an equation. And we have the equation this way. You can move like this. From here, you can go there. And from here now, I don't know where you're going to go to because you don't know whether these are equal. So, right. All right. But what you say is a true statement, but I don't know whether it'll help you to solve the problem. Okay. There may be some other ways of doing this thing. I had 2 ways of doing it. When I send you the solutions, you'll be able to see both ways.
Excuse me, sir. Can I say something?
Yes.
I've also noticed that CAB is also equal to CBA.
Okay, C, A, B. Say it again.
CAB is equal to CBA.
Yeah, but that is why we said this is X. Because CB equals CA. These are radii. Therefore, this is an isosceles triangle. And that's the first thing we said was the y is actually equal to x. The reason for that is that this is an isosceles triangle. If two sides of a triangle are equal, CA equals CB, then the angles opposite those sides are also equal. That's a theorem in geometry. So that was used already to conclude that y is equal to x. Okay, that's what you notice is correct, but that was the first thing we noticed, and from there we went on to get to this equation. Okay, any other statements? All right, the next problem is a kind of problem which involves volumes, and I don't like this kind of problem. It's a kind of a messy problem. You got a rain gauge in the shape of an inverted pyramid with square base, has height 300 meters. The square has side 100 meters. And then you have a square base right prism. So you got a pyramid on the one hand, and you got a prism on the other. So you got a pyramid and the square base. So a pyramid looks like this. Square base. Something like that. And a rain gauge, this thing is upside down. So it looks more like something like this. Okay. Now it's a rain gauge. So the water can fill up into this thing here, but it's got a sharp point here. And then you also have this thing, the height of this is 300 meters. And the square has got side 100 meters, 100 millimeters at least. So you got this square here whose sides are known, and you got the height of the pyramid. So those two things are known. Then you got another statement which says a square base right prism. Now that looks like this. A cube is an example of that, but it need not be a cube. It could be a long shape like this. It's a right prism, and it's got a square base. It's not a pyramid anymore. And this thing here has got length 100 meters, 100 millimeters. So it's shorter than that by a count of 3. And the base has side 100 meters. So this square is also the same as that square. These two squares are identical. So the base of the pyramid and the base of the prism are identical squares, but the height of the pyramid is 300 and the height of this is 100.
So the height is also 300.
Oh, the height is also 300 here? The base has side 100 meters. Oh, this is also 300. Oh, okay. Sorry. Thank you for that. So both have got the same height and they both got the same square base. Okay. Now, if you empty the rain gauge into the empty square base prism, so this is empty and the rain gauge is filled to the brim. So this is filled right to the brim. If you empty it, the question is now, what will the height of the prism reach? So this thing goes up to a certain height when you empty this. This is obviously got lesser water or lesser liquid than this one. They both got the same square base, the same height. There's a lot of stuff missing outside. Okay, now this is a problem with volumes, and the volume of a pyramid is, anybody knows what's the volume of any pyramid?
Are given in the question. The effort area.
Oh, they give it to you. Yeah, okay, that's very nice.
Times height.
No, I know.
Yeah. Okay, but it's nice to know this as a fact. 1/3 area of base times the height. It doesn't matter what the base is. That's a remarkable thing. It could be a circle, or it could be a triangle, or whatever it is. The volume of a pyramid is always 1/3 the area of the base times the height, right? Regardless of the shape of the base. That's a very remarkable fact in geometry. Okay, so you can calculate this volume. It's 1/3 the area of the base times height. And what is the volume of this?
The length times width times height.
Yeah, okay. So you can say it also as the area of the base, which is length times breadth times height. So this is area of the base times height, and this is 1/3 the area of the base times height. So this volume here should be 1/3 the volume of this, right? So when you fill this thing up, you should expect, if this is 300 millimeters, I would think that this will only go up to 1/3 of this. This volume, the volume of this is 1/3 the volume of that. So to get 1/3 the volume of this, the height has to be decreased by 1/3. So this, I can say mentally, this should be 100. Right? The volume of this 1/3 area of the base times height. This is area of base times height. So this volume here is 1/3 the volume of this. And the 1/3 of the volume of this will be, you'll have to divide this thing up into 3 equal parts. So you just divide the height into 3 equal parts, and this is where it will fall. Then the second part of it says, if the rain gauge is filled to the height 150 millimeters. So if you went, it'll still be a square here, like that. But now the height is 150. Then the question is, what will the height of the water in the prism reach? This will, you got a lesser amount of water now, and the amount of water is, the height is just, it's half of this, right? Half the original. So it's 150. But what happens is that the square also is decreased in size. So this square add side 100, then this square here will have to have a side 50, because we are only going halfway along this. See? So if the height of this is 50, then all the sides of this will be half of that. I'm not going to go into detail with that. We just have to assume by intuition that this side here is all 50. So the volume of the water here will be 1/3 50 squared. See, the base will now be 50 times the height of that. That's the volume of the water. And you want to fill this thing up here. So you know the volume of the water here, right? And you want to know what the height is. But this again will be a prism here. It will be a smaller prism. What if the height is capital H? It will be H times the area of the base. So the area of the base times whatever height the water goes up to will be the volume of the water that is coming from this pyramid. And the volume of that water is 1/3 the area of the base times height. So the height can be calculated from this equation. Okay. So I'm not going to go into too much of detail with that. This is just, it is not so much a problem solving exercise. It's more applying a formula and getting somewhere, which doesn't excite me too much. Okay, if you just excuse me for a moment, my room is dark. All right, so that is not so much a problem solving exercise, but it's a calculation exercise, which I went through quickly without too much of fuss and bother. So let me just clear all the diagrams and get to the next problem. So we now go on to problem number 11. All right, now we are getting to problem number 10. We're getting into more difficult problems. So on some square of an infinite grid, okay, the grid you can see, they say it's infinite means there's no grid which is infinite. What it's saying is that you've got a large number of squares in that grid. There is a cube which covers the square exactly, as you can see. Now the top face is red and the other faces are all white. Okay, in one move, the cube can be turned over any edge so that it covers a neighboring square. And this is going to be quite difficult for me to explain, and even for you guys, but let's hope you figured it out. Okay, so you can make one move, you can just turn it over, flip it over, and like for instance, if it's flipped to the square here, all right, so you have to move it anti-clockwise and it falls flat back there. Then the red square will be facing the square here. Right? The red square will be up like that. Okay, so like that you can flip this thing in any direction. Right? Now determine whether it is possible to move the cube such that it is returned to the initial square with the red face at the bottom after exactly 218 moves. So you want this thing to come back to the original position after 2018 moves. Would you be able to do it? Okay, obviously you can't go all the way up to 2018. Let's see what happens in the first few moves. I want to get it back to the original position, to get it back to where it is here. With the red face at the bottom. Oh, okay. The red face must be at the bottom.
I can say something about the 2019 moves. It would not be possible because if you need an even number for it to get back to where it started, an uneven number would thus mean that it would be on a different square when that uneven number when it reaches that uneven number.
All right, so you're saying 2019 is not possible because you'll have to have an even number of squares. Okay, again, as I said, Andreas, you have to say why you say that there must be an even number of squares.
You have to
explain
number
it
of
before you say it's even.
moves.
You have to say it before you say it's an even number of squares, you must explain
If you were to go in any way, any moves, and then go back, you will, if you will have like, when you hit the starting square, you will have used an even number of moves. Like, for example, you just go back and forth in that time. Each time you hit back there, you'll get an even. If you were to do and square, each time you get back there, you'll have an even number. Well, if you were to do dots and straight line and come back, you'll end with an even number. No matter how you want to try to do it, you'll end with an even number. You will only end with an uneven number if you can go diagonal. Or be able to end with an uneven number if you will be able
Andreas,
to go diagonal.
I've got your picture. Right, but I think basically, for instance, now to get back to the original position here, you could do it like this. You could go this way, but you want the red face to be at the bottom. Right? The red face is at the top at the moment. Right? But if you go back to exactly the same position, you got to go down one this way, and then come back again. Then you'll need two moves to come back to the original position. right? And you can go back and forth. So you can have 2 moves or 4 moves or 6 moves and so on to get back to the original position. So to get back to the original position, you'll always, you can make 2018 moves. That's not but that's not the problem. The problem is that you want the red square to be at the bottom of this thing, right? So let's see whether you can get to the bottom and how many in how many different moves can you do that? Well, what's the least number of moves you can get to the position where this is the red square is at the bottom? Now that question needs to be answered. All right, and we can't just sort of waffle around and say even. You have to explain what's going on here. If you turn this thing once here, then you've got the red square facing us at the moment. And then if we turn it once more, then the red square is at the bottom. But now it's not in the original position. And then you have to turn it away this way again, go back this way. The red square will still be at the bottom. And then you go up and go up. And one more move. Well, I'm not going to go through this thing, but it turns out that you can get back to the original square in 6 moves with the red square at the bottom. You can just think about that. I've actually worked it out here somewhere.
Sir, I found a path.
See, after 6 moves, you will be at the bottom of the original square. The red square will be at the bottom. So after 6 moves, you can get back to the bottom. And after that, you do what Andreas has suggested, that you just go back and forth. So you got 6 moves, you can get to this. Then now you can move it one direction and come back to this. That will make 8, and you come back to the to where you want to be. And another 2, you'll be where you want to be. And you keep going on, and eventually you can come to 2018. Somebody made some statement. Can I just get that one, please? But you have to show that in 6 moves, you can get back to the original position with the red square at the bottom. That you have to demonstrate. You require a certain amount of geometrical intuition to keep track of this thing. I did have without the geometric intuition, I've used something here like this, some bottom red and so on and so forth, to try to see whether it can be explained. You can have a look at that. But now the question is now whether you can do it in 2019 moves. Now what Andreas is saying that this can't be done because you'll have to have an even number of moves. But I would like to know why he is saying that.
It's because it has to be divisible by 6 because it takes 6 moves. So you'd have a certain amount of cycles to get through.
Well,
the
6 will get you back there, but you don't have to go through the same 6 all over again. As I said, then from there you can go this way, back, this way, back, this way, back, up and down, up and down, up and down to go all the way to 2018. Right, but
Prof, may I try?
I think maybe this one here would see, it can be done in 2018, right? So once you are here, you make one more move. No, actually that wouldn't be an argument.
So
Yes.
I believe it's because if you take a step away from the original starting point,
yes,
you would have to take one step back for every step you take away from it. should be an even number.
Okay, that seems to be a reasonable argument. To get back to the starting point, you have to have except that you can go in any direction, so it's not very clear. If you go along one straight line and you say, okay, I go on to a straight line, I go up to the square here and retrace my steps, then you have to have double the amount that you had to get here, which makes it an even number of moves. But if you're going here and you can going there and you're going down here and you're going this way and going that way and getting back, it's not very clear that you're going to have an even number of moves.
I believe it would still apply, though, because
still apply, but we have to give an argument. Yes.
Let's as an example, I could say if you move twice to the right and let's say 2 times upwards, you would have to move twice to the left and 2 times towards the bottom to get back. Because no matter which direction you move, you'll just have to mirror it in the opposite direction.
All right. Okay. What you're saying is absolutely correct, but I'll give you a very nice proof of what you are saying, right?
Basically,
it will be very much clearer.
the chessboard effect. Can we say the chessboard effect for it?
That's right. That's right. In other words, you color this thing as black and white, like a chessboard. Right? So what it means is that if you color it like a chessboard now, every time you make a move, you're changing the color of the bottom. Do you agree?
Oh, yeah.
Right? Each time you move, you're changing the color. So to get back to the original color is either white, black, white, black, white, black. Each move is going white, black, white, black, white, black, white, black. And if you want to come back to the original one, you have to have an even number of moves. Black, white, right? That's one move. From the next move, you come back to black. So to come back to black, you'll have to have 2 moves. Each time you come back to black, you have to have 2 moves. So that you can think about it and ask yourself how you can explain that so that it becomes, okay, I've got just 14 minutes. So I'll leave you with that thought and you try to see how you can argue with this so you can come back to this. And later on, when I send you the solutions, then just check to see whether that solution is reasonably explained. I don't guarantee that I will explain it in full. All right, question 11 now. We've still got another 5 questions to go. Okay, so we might finish probably by 6:30. And let me see how many people are still with me. Oh, good. Everybody is here. All right. So nobody's running away. Oh, well, one person seems to have left now. Okay. Let's just get back to this. Now, this question 11 is an interesting question. What is it saying? Question 11 is saying, in an auditorium, each row from row 2 onwards has 1 more seat than the row in front of it. So let's just draw this diagram. So you got an auditorium and you got a row here, and you got 1 row which is slightly longer. Each row has got 1 more seat than the row in front of it, right? So you got an examination conducted in an auditorium which is looking like this. Now students may sit in any row, but they must leave at least 1 seat open between themselves and the next student in that row. Now there can be 2 possible reasons for this. One is because of COVID-19 regulations, and the other one is to prevent copying. Okay, so you distance yourself reasonably from the next person. Now, if there are P seats in the first row, so in the lowest row, you got P seats. Okay, so the next one will have p plus 1, p plus 2, and so on. Right? Find the maximum number of students that can be seated in terms of p. Maximum number of students. Now, the maximum number of students can be obtained only when you have exactly one seat separating two people. So we'll try to work towards a situation where you've got exactly one seat which separates two people. All right, now there are two possible cases. Okay, let's see now. Anybody wants to say, if I have, for instance, if I have p empty seats, how many people can you put in that row, the largest number? That's the question.
I'm not sure, but I think it would differ if it's odd or even.
Yeah, it will. Okay, let's try that. Let's just follow that what you're saying. So suppose I have p equals, for instance, 7. How many people can you put in that row? Maximum number. Okay, let's do it. Okay, somebody said 4. That's quite right. Let's see why.
I used the formula p divided by 2 minus 1. Plus 1, sorry.
Not quite. We're nearly there. But let's look at the 7 case. You can put a person here, put a person here, and put a person there, and put a person there.
If you were to like p equals and even at p equals an
Andreas,
odd.
just be silent. Don't talk when I am speaking. When I have finished, you can come and interrupt, okay? You're doing this all the time, and please don't do that. I will give you a chance to speak. You can raise your hands, or you can tell me when I've finished, sir, I want to say something. Don't interrupt me with your own train of thought. All right, let's do this again. If p is equal to 7, you've got, this is the maximum number you can put. You fill this person, this person, this person, this person, and then you get 4 people. Right. So now how do you get 4 from 7? That's an odd number, right? If you had 9, then you can put another 2 squares, and that'll give you 5, isn't it? Okay. So, Christina, I think you said you divide p by 2 and add 1 to it. If p is an odd number, if you divide it by 2, you're going to get a half. Right? And when you add 1 to it, you're going to get a half of that. So what you really want to say is that you add 1 to p and divide it by 2. Agreed?
Yes, thank you.
Right. So it's just a slight modification. You add 1 to p and divide it by 2. So if p is odd, then the number of people that can sit on that row is p plus 1 over 2. Andreas, now I'll give you a chance to say what you want to say.
Well, for the p is, if p is odd or even, we can just say p over 2 and then round it off to the closest integer.
All right, okay, this has got nothing to do with rounding off the integer. All you are saying is that p over 2 need not be an integer. And when you add 1 to it, you're not going to have an integer. All right, which I've just explained. So if p is odd, then you have, this is the number of people you can put in. And if p is even, how many people can you put in?
P divided by 2.
That will be easy. It's p divided by 2. Right? If I've got 4 people, you can put only that, or that. So you'll have half the people. All right, so now that makes it rather complicated, because the question is, now you've got 20 rows here. And you want to know in terms of P, how many people can you put over into this altogether?
Could I suggest something?
So it can be quite complicated, because you have to consider odd and even cases, and you're going to take 20 rows and so on. You don't know whether P is odd or P is even. So you have to start with P odd and work out something there, and then try to work out when P is even, work out how many there are. And that takes a fair amount of time, because each time, if you started off with P as odd, for instance, then this becomes even. And then that becomes odd, because you're adding one each time. And then you got different formulae for each one of them. In some cases, you'll halve it, and the other cases, you add one and divide by 2. And then you have to add all these 20 numbers. All right, you can do it like that, which I did, and I found it to be quite cumbersome. But I found something quite nice in this. Okay, there are two people who raised your hands. Can you speak, any one of you?
Well,
all right. Okay, since there is nobody.
It is 20 plus 1.
There's a problem with the mic, and we can't hear a single word you are saying. All right, let's just wait a little bit, and then maybe it'll work out nicely. What I found is that we have a general way of dealing with this thing, where you say that let's take any two consecutive rows and see what happens. Right. And suppose you got in one row, you got X people. So the next one will have X plus 1. Right. I want to find out how many people are there all together in this situation. If we got X here in the smaller row and X plus 1 in the larger row, how many people have I got all together in this scenario? All right, now there are two cases. If X is even, right, now tell me how many people you got all together. Anybody wants to answer it? Let's look at the bottom one. How many are there? We are taking the case X is even.
That is X divided by 2.
Right, Mehmet, correct. X divided by 2. Okay. And the other one, how many students will you have in that one? Anybody wants to say?
X divided by 2 plus 1.
X plus? Say it again, I can't hear you. Joshua?
X divided by 2 plus 1.
I can't hear you. Can you just say it more loudly? X plus?
I think he's saying X divided by 2 plus 1.
X divided by 2 again.
I think he's saying X divided by 2 plus 1, but I'm not sure.
Well, yeah, I think it's right, but
X plus 1 divided by 2.
Yeah, Nakshatra, what are you saying?
X plus 1 divided by 2.
Isn't it X plus
not quite.
2?
Not quite. You see, X plus 1 is the number of people here. You have to add 1 to that and then divide by 2. That's what we said. If P is odd, add 1 and divide by 2. Okay? Agreed? Because now it will be odd, you see, X is even, so this is odd. So in the case of an odd case, you have to add 1 and divide by 2. So X plus 1 divided by 2. And this is X plus 2 over 2. So this is X over 2. Or actually, you can just do it like this. Common denominator is 2. When you add up all the numerators, you get 2x plus 2. Right? And 2x plus 2 divided by 2 is x plus 1. So when x is even, you get a nice formula. The total number of people in these two rows will be, will be x plus 1. The lower number, or it'll be equal to the higher number of the two. Right? that is when x is even. Now, when you have x is odd, okay, there are three people who raise their hands. So I'm going to ask you, what's your contribution? Somebody raise their hands.
I wanted to suggest another way of doing it.
Okay, Mehmet.
I didn't solve it, but I think we could solve it by adding them all up. P plus 1 plus P plus 2 and so on.
Well, no, it wouldn't give you the answer. I can tell you that. All right, that you just give me an answer which is like an intuitive answer, right? So it wouldn't be the correct one, and you are trying to guess an answer, but it doesn't work. Okay, let's just go on with what we are saying here. If x is even, we know what it is, and if x is odd, we need to calculate how many people there are altogether there. Right, if x is odd, can you tell me? The lower one, what will it be? What will this be if x is odd? How many people are here?
X plus 1 divided by 2.
Correct, right, x plus 1 divided by 2. And if x is odd, then this becomes even, right? So how many people are there here?
X plus 1 divided by 2.
Again, when you work this thing out, they've got the same common denominator. The numerator is 2x plus 2 divided by 2. And interestingly, that's also x plus 1. So regardless of whether x is even or odd, the total number of people in two consecutive rows is going to be the larger of the two. See? So if you make that observation, then you can solve this problem quite easily, because what you do is divide these 20 rows into groups of 2, right? The first one, and then, sorry, I'm not using my whiteboard here because it's too cumbersome. Okay, you have 10 groups of 2, and then in each one of them, we know what the number will be, and now we should be able to calculate it. So let's start from the bottom. You got P plus 1. How many people are here altogether here?
P plus 1.
P plus 1, correct. Right, let's get to the next group. How many people are there altogether here? We're counting in twos as we're going from the bottom to the top. The number of people here was P plus 2, right? And the number of people here was P plus 3. Agreed?
Yeah.
So you're taking the larger of the two. Because our formula said that if you've got two consecutive rows, regardless of whether x is even or odd, the total number of people in those is going to be the one number of empty seats in the larger one. So the number of empty seats in the larger here will be P plus 3. Okay, and now you can go on. The next pair will be what?
P plus 5.
Right. Now we don't have to decide where it's ending. All we have to say is how many terms have you got here?
10.
10 terms, because we're breaking them up into 10 groups, and each group of 2, we are saying how many students are there. So there are 10 groups of 2, so there are 10 terms. Now you're adding all this. What will that give you? How many P's are there?
10.
So the P's will give you 10P. And what about the others? It'll be 1 plus 3 plus 5. How many of these?
10.
10. This is the sum of the first n odd
100.
numbers. And I think I told you guys, if you were in the previous classes of mine, that a very interesting fact about the sum of the first n odd numbers is that it is equal to n squared.
Oh, yeah.
1 plus 3 is 2 squared. 1 plus 3 plus 5 is 3 squared. Right? You can calculate the whole 10 and add them up, and you'll get 10 squared. You can do that. You can add them up. But if you knew that the sum of the first n odd numbers is n squared, then you got the sum of the first 10 odd numbers to be 100 without any further calculation. So this is the maximum number of students you can have in this auditorium if the first one has got P. Right. So this one you have to figure it out. It's a tricky one. If you worked it out, you first have to figure out how many people there are in a row, but the formula changes when it's odd or even, and therefore it becomes a little bit tricky. But if you do it step by step instead of having 10 pairs, then it can become quite cumbersome. I think I did it like that originally, and then after that I found that it's much easier to work it in pairs. Now you see, this is what I got, a rather very complicated thing here. As you can see, that's what I did here. Oh no, this is the one that I got. But you see this one, when I went through from one row to the other, it became, I had to use some formulae and all that, but eventually I came to 10p plus 100, which was the final answer, but it comes after a lot of calculation. So there is a way of doing this thing without doing too much of calculation, and that's what problem solving is all about, to find some clever way of working out the problem without having to do too much of calculations. Oh, this is the answer. Oh, an alphametic. Each different letter represents a different digit. Now, you guys are familiar with the alphametics?
Yes.
I think every math student should have, anybody who's interested in problem solving would have tried some alphametic or the other. Now what an alphametic is something which has got, as they say, alpha is the alphabet and metic is like arithmetic, which is numbers. So you got an arithmetic of numbers here. These alphabets represent numbers. So each alphabet represents a different number, and you want to know what these numbers are. So how do we do it? So what we are doing is we're adding these two, and you're getting this answer. So S plus O is T, and so on. And sometimes you might have to carry over. Whenever you're carrying over, you can only carry over one. You can't carry over two. You'll appreciate that, right? Because two digits, when they're added, right? You can't have it being more than 20 or more. So you can only carry over one. So the carrying over is usually one in this problem. So that should help us a little bit. You got a 4-digit number and you got 3-digit number. So what can you say about S?
It has to be 1.
S has to be 1. You got a 4-digit number plus a 3-digit number. You can't get anything being more than 20,000. Right? It has to be somewhere in the 10,000s.
And then D has to be 9.
Then D has to be 9. Yeah, D has to be 9.
H has to be 0.
H will be 0.
0.
Right. Okay. So now we have these. You got TOO, and you got AYS. Right. Now there's an interesting case here. You see, O and the T, and here you got T and the O here.
Well, so O plus 1 is T, and there T at O, which is below each other, which means
Oh, wait a
A
minute.
has to
Just
be
one moment.
9.
Just one moment. The S we should have filled in. The T and the O are here. D-A-Y-S. S here is 1. Yeah, we should fill the S. Right. Okay, now we can proceed.
Well, then is the O, 1 plus O is T, and then the only way to get T and O, like T and then O at the first thing is by A has to be 9, then we can go from T to O. Like 5 plus 9 is 4 on or 14 and so it's. So
Right.
A
Now,
has to be
okay, Andreas,
A
9.
that's a very good observation. Anybody else wants to expand on that? Do you understand what he's saying?
Not really. I'm quite catching.
And O brings a remainder over. So then A has to be 8.
I said anybody else, Andreas, if you didn't hear me. All right. What Andreas is saying is quite correct. Let me just explain what he is saying. He is saying that 1 plus this is equal to that. That means that these two are only 1 apart. This is 8, this is 9. This is 7, they're only 1 apart. So now these things are reversed here, T and O, but you've got now that the smaller number is, if you got 8 and 9, you got the larger number here, and you got the smaller number here. So if I had 7 and 8, this becomes 8 and 7. But they still differ by only 1. So if you are adding something, you got 8 and you got 7, right? You'll have to have a 9 here. If I got 7 and 6, I'll have to have a 9 here again. 9 plus 7 is 16. Or if I got 5 and 4, I'll have to have a 9 here. Right? No matter which way you look at it, if this is 1 more than this, but you can't have a 9 here. Right? And then Andreas decided you can't put a 9, but it's possible you can have a 8. That's the only possibility, because there's a carrying over. Right, Andreas? Is that what you were saying?
Yes.
Right. And then after that, now it's a question of trial and error, because now you've got quite a few numbers. You've got 8 and 9 and 0 and so on. We can try other numbers here. I can try 7. And remember now that the T is also here. Whatever comes down here has to go there. So if I make this 7, for instance.
So 7 won't work.
This will be 8. It won't work. We already got 8 here. So we're not allowed to put. So we can try a 6 here.
O must be 6 or lower.
Let's try a 6. If you got 1 plus 6 is 7, so this has to be 7 and 6 here. Okay. 1 plus 6 is 7, but we are carrying over. Right? And this T is going to be the same as that, you see? So it's like that. But the 6 is repeated. So you got a 6 here. TOO. So what are we going to put here now? And you need to carry them over.
Well, the 6 won't work, because then Y has to be 6 or more, and it can't be 6. If it is 7, it gets cancelled out. If it's 8, it gets cancelled out. If it's 9, it gets cancelled out. If it's 5, it then the S is a problem. If it's 4, then that becomes 0, which is a problem. So
Yeah, so you
6
can try
won't
all the
work.
numbers here. You'll see that none of them work. You can try
So
4
we
here.
will have to go with O equals 5 T.
Okay, Andreas, be silent now. Right, so if you try anything less than 4, then there's no carrying over. So you have to use numbers from 4 onwards. But if you put a 4 here, right, there's no carrying over at this stage. You're going to get a 0, which is not allowed. If you put 5 here, you're going to get a 1 here, which is not allowed. You're not allowed to put 6. And you're not allowed to put 7. You're not allowed to put 8. You're not allowed to put 9. So you can't put anything here. No matter what you put, you're going to have a problem. So 6 is wrong, right? And this is where Andreas was rapidly heading towards. And so this has to be 5. And then thereafter, you can work this thing out. I'm not going to do anything more than that. You can figure out how it's done. But there's a logical way, as you see, of solving these problems, right? By looking at the numbers. You're starting from somewhere and slowly build yourself up to something else. Okay, so we have let's get on to problem number 13. Problem number 13, now it's getting a bit more difficult, and sorry, we are going into extra time here, but I just hope that you can bear with me. Look, we can stop here because we're planning to have 3 more meetings. So we're going to have, the next time we meet, we're going to do 13, 14, and 15 of this, and then we'll do 2019 in the and some of 2019 in the second meeting. That's on Saturday, right? If we're going to meet again on Saturday. So I'm going to be quite demanding because you are writing this exam on the 28th, and there are only 4 sessions. If I do it twice a week, I'm quite prepared to come on Thursday and Saturday this week, and next week again Thursday and Saturday, and the week after that you will be writing the exam. So we've got 4 sessions, and I'm going to meet you again on Saturday from 10 o'clock to 12 o'clock. Previously, we used to meet at, the juniors were not involved in that one, but we're going to meet from 10 o'clock to 12 o'clock because these days I've become quite lazy. I sleep too late and I do other things in the morning. So we're going to meet at Saturday at 10 o'clock. I'm going to send the link through to South African Maths Foundation, and they will post it on the board, or they'll send it to you. All right, so do me a favor, in the chat column, you can write down your email addresses so that I have that with me, all of you. Just give me your email addresses as well as your name, initial and surname, or even your full name and email addresses. Do it now in the chat column, please, because I don't have any record of the people who I'm talking to. So if you can help me with this, at least I have a record. Some people have left, unfortunately, but
Sir.
Yes. So, sorry, who was that?
Sartin.
Cyan. Yes, Cyan.
Can you please show me the answer to the last question again, quickly?
Oh, the answer to the last question. What was that? Oh, the answer. Oh, there it is. It's 10,500. It works at 5, son. Okay. We went through all of these except that the O. We were trying out different values for O, and 6 didn't work, but 5 worked.
Thank you.
And it needed to be 5 or higher, so automatically it has to be that. Okay. All right, so we will meet on Saturday at 10 o'clock. I'll send you the link. And please, as I said, if you just give me your names on the chat column, I'll have that on record. Thank you very much, guys. Is there anything that you want to say?
Thank you for the lesson, Professor.
Andreas, I must thank you for your input. You're a very active person, but just be a little bit cautious. There are lots of people in the classroom. We've got 50 people, and one, and secondly, we can't spend too much of time on each question. So wait until I finish, then you can make your input. You always have something valuable to contribute. Okay, right, Christina, I've got your email. Thank you very much.
Thank you for the lesson.
Okay, was it Almaz?
See you
Okay,
later.
Almaz, bye.
Thank you.
Okay,
Bye.
Mehmet.
Bye.
Thank you. Bye.
Okay.
Thank you. Bye, sir.
Thank you.
Okay, bye, my
Thank you.
dear.
Bye, sir.
Okay,
Bye.
Nakshatra, bye.
Bye, sir.
Bye, Pranay.
Yeah. Thank you, good boy.
Bye, Jo Marie. Have a nice weekend.
Hello, Diet.
Thank you so much, sir.
Bye, Akhil. Or was it Madia? Madia, was it Madia?
It's Mahdia.
Mahdia.
Yes, it's Mahdia.
Hey, how come your wadis have got so many people? You got Amara,
I don't know,
sir. You got a Talia, now there's a Mahdia. What grade are you in, Mahdia?
Yeah. I'm in grade 8, sir.
Grade 8. You got in the third round.
Yes, I did.
You got in the third round, Mahdia.
Yes, sir.
Very good. From grade 8. You are following in the footsteps
Thank you,
of your
sir.
illustrious family. I think
Thank you, sir.
the parents are doctors, if I remember correctly, Amara's parents.
Yes, they are.
Both of them?
Yes, both of them.
Yeah,
sir.
I had the privilege of meeting them when I was in Pretoria some time ago, and they were kind enough to give me a gift, which I normally don't accept, but they were very sweet. They came and gave me a gift. And then there's Tasneem. I think there's a Tasneem Wadi.
Taskin.
Huh?
Taskin, sir.
Yeah. So you are in the line of the Wadis. Are those other two your sisters and brothers?
Yes, they're my sisters.
Wow. So you got a very intelligent Wadi family. Give my regards to your parents.
Okay, thank you so much, sir.
Okay, bye, Mahdia. Sorry, I was having
Bye,
this conversation
sir.
with the others, and I should have taken this recording off